now, in the part 2 of the lecture, we went through a fairly detailed explanation as to why the wind speed in the Ekman layer is going to be increasing with respect to height. It's all going to be subgeostrophic, less than geostrophic, but it is increasing with respect to height. Now we're going to start trying to pick through what would the direction of the wind be in the boundary layer under these conditions of the air being well mixed. In other words, what will we be able to say about the direction of the winds when they are in Goldberg-Mohn balance? What is the Goldberg-Mohn wind approximation here? Again, remembering that your book foolishly calls this geostrophic wind. Alright, so if we look back, I just literally swiped some of these slides from the geostrophic wind lecture. If we look back at our analogy, the diagrams that we drew about the geostrophic wind, where we had an air parcel, I just drew it on Nebraska so you understood that we're looking at like on a map here, and I've got some isobars, those blue lines there, with lower pressure up near like northern Nebraska and higher pressure down towards southern Nebraska. Well, we had a pressure gradient force vector, which I have in red there, pointing towards, perpendicular to the isobars, towards low pressure. I have the wind vector because it's geostrophic. That is, we're up in the free atmosphere or something like that. That wind vector is purple, I guess, and it is parallel to the isobars with low pressure to its left and higher pressure to its right. And then the Coriolis force vector, which is green, has to be 90 degrees to the right of the velocity vector, and it is equal and opposite to the pressure gradient force, so that the two forces add up to 0. Alright, what if the wind is subgeostrophic? Now, I want to explain what I'm doing on these slides here. So I have now changed my velocity vector. See, the purple vector there is now shorter than it used to be. Now, to help us keep referring back to comparing what we're drawing now to geostrophic, what I did is I kind of left a little purple shadow of what the wind vector looked like when it was geostrophic. See how like the geostrophic wind vector there is still there? It's just kind of faint. Okay, that's what I'm trying to do there. That one is still going to be there just sort of for reference. So I've taken the wind vector here and I've made it shorter to make it subgeostrophic. But here's the deal. Remember, what determines the strength of the Coriolis force is the speed of the wind. So if I've made my wind subgeostrophic by adding friction or something like that, I can't have that same long Coriolis force vector that I had before, because the Coriolis force, the magnitude is determined by the speed of the wind. So see how I did the same thing with the Coriolis force? I made it shorter, and to help us compare it to what we had when we were talking geostrophic, I kind of left like a shadow or a faint version of the original Coriolis force vector there. Okay? I'll walk you through all that. Alright, so now I've made my wind subgeostrophic and slower, and by doing that, I had to make my Coriolis force vector slower. But here's the deal. We really wanted the forces to add up to 0, but if I kind of highlighted them there with blue glow, clearly now that pressure gradient force vector, which has not changed, plus that Coriolis force vector, which is much smaller, clearly they don't add up to 0 anymore. Oh, we got a problem here. Clearly they are no longer, the Coriolis force and the pressure gradient force are no longer equal and opposite once we are in some kind of subgeostrophic condition here. And in fact, what's going to happen is the pressure gradient force is a little bit stronger than Coriolis force. You can think of it as the pressure gradient force is going to win a little bit. It's going to turn the wind, pull the wind a little bit towards the area of low pressure. See how I kind of pivoted the subgeostrophic wind is no longer parallel to the isobars. It has turned a little bit. In fact, if I zoom in with my magnifying glass here, you can see how the wind, which is that purple vector there, it's still mostly following the isobars. I mean, it's still kind of following, but it still has low pressure to its left and higher pressure to its right, but it does cross the isobars a little bit. It is kind of headed at a shallow angle across the isobars, still mostly sort of following them, but kind of going across the lanes of traffic, if you will, is kind of crossing those isobars a little bit towards low. And notice that the Coriolis force vector, which is that green one there, again, you can see how it's different from when it was geostrophic by looking at that kind of faint green one that's in there. I mean, it's still 90 degrees to the right of the motion of the wind. I just had to turn it just like I turned the wind. But notice it's a lot smaller than it was when it was under geostrophic conditions, and that new Coriolis force vector is a whole lot shorter than that pressure gradient force vector, the red one. We got a problem here then. We wanted the forces to add up to 0. So clearly, the Coriolis force vector and the pressure gradient force vector here are not adding up to 0. I have them highlighted in kind of a blue glow there to help you see which two I'm talking about, because I realize the diagram is going to get cluttered here. Alright, well, they clearly don't add up to 0 here, but we have one other force. Remember, friction. We always draw friction as being 180 degrees against the direction of the motion, so since the purple vector there is my velocity, then I'm going to put in friction as being 180 degrees the opposite direction. It's that black vector that I have in there. It's also glowing blue, just so you can see which forces I'm talking about here. Now, that red vector plus the green vector plus the purple, I'm sorry, the red vector plus the green vector plus the black vector there do add up to 0. A hard thing for human brains to sort out, but it will add up to 0. So our pressure gradient force plus our Coriolis force plus now friction add up to 0. There's a three-way force balance going on here, which is very hard for human brains to sort out. Okay, it's very hard for you and I to look at that and say, oh yeah, those add up to 0. But they do. Okay? So, just by making the wind a little slower, which back in part 2 of this lecture we saw why that was, right? Because of mixing of low momentum air from down at the surface layer up into the Ekman layer, we ended up with winds in the Ekman layer that are slower, subgeostrophic, but also turned slightly towards the area of low pressure. They're not exactly parallel to the isobars, they've turned a little bit to the left, and they're slightly crossing the isobars towards areas of lower pressure. Now let's actually go back and look at that profile of the winds that we made there and figure out what direction they'll be at each of these heights. I mean, like if I go up near the top of the Ekman layer, see how I have highlighted in red the wind vector that's up near the top of the Ekman layer there? Well, those winds are only a little bit slower than geostrophic. They're only a little bit subgeostrophic, which means we've really actually only reduced the Coriolis force a teensy bit. And if I actually tried to make a diagram like what we've been looking at so far, what we would end up with is winds that are really only a teensy bit different than the geostrophic winds. I mean, my wind, my Goldberg bone balance wind, that would be my estimate of what the real wind was doing in the boundary, in the Ekman layer, would be like that purple vector. And you can see I have, again, that sort of shadow of the purple vector, that faint purple vector. The faint one is the geostrophic wind, and you can see my wind up here near the top of the Ekman layer really isn't all that different. It is pivoted a little bit to the left. It is slightly crossing isobars towards low pressure, but not really all that much. Okay? On the other hand, if we went to a height more towards like the middle of the Ekman layer, which I have highlighted there in red, well, here those winds are actually quite a bit slower than the geostrophic wind up there in the free atmosphere. You can see its vector is a whole lot shorter. And since the Coriolis force's magnitude is determined by the speed of the wind, the Coriolis force has been reduced quite a bit. And in fact, if we went and worked through our force balances and so on, we'd end up with a map something like this, where we end up with winds that are actually quite different from the geostrophic wind vector. Remember that kind of faint purple one is geostrophic, just to keep reminding us what the geostrophic wind looked like. And the dark purple vector shows us what our wind here in the middle of the Ekman layer is going to look like. And you can see that these winds are actually crossing the isobars at a greater angle. They are turned more towards low pressure. And in fact, their winds are even slower, as we learned about in part 2 of this lecture. And in fact, if we went even down, almost all the way down to the surface layer in the Ekman layer, near the bottom of the Ekman layer, here these winds are, like the one I have highlighted in red there on the left-hand side of the screen. Well, that wind is a whole lot slower than the geostrophic wind up there in the free atmosphere. And so now our Coriolis force has been way reduced, practically to nothing. And in fact, if I worked through my force balance for such a thing here, I would see, again, if I take a look here, my geostrophic wind vector, remember, is that faint purple one there. And my new wind, my Goldberg bone balance wind down here near the surface, well, near the bottom of the Ekman layer anyway, is that dark purple vector. And you can see it's a whole lot different. It's very different from the geostrophic wind vector. It's crossing the isobars at even a bigger angle. I mean, it's practically going in the direction of the pressure gradient force at this point. And the Coriolis force is way small, and the speed is really low. Oh, neat. See how at different heights we ended up with different directions of the wind just by adding friction? It's so weird. I mean, all friction can do is slow an object down, and yet in the Ekman layer, it does result in a change in the direction as well. And the direction that the wind will be going is well predicted by the so-called Ekman spiral. You might have been expecting this word, Ekman spiral, since we were talking about the Ekman layer. And here's a drawing of the Ekman spiral, and I totally get it that we're not ready for this spiral yet. We need to get it set up, because I mean this diagram here, the labels are weird. Which ways, what are we looking at here, etc. So what I'm going to do here is I'm graying that diagram out. I'm kind of blurring it out there, and I'm going to draw something on top of it that will help illustrate what's going on, okay? So what I want you to do, to understand is here, I'm going to be making a map. And on this map, here's Nebraska, just to help you understand it's a map, I've got an air parcel at some location. That air parcel is indicated there with that blue dot. And this is going to be my location or whatever. And I've drawn in red here some isobars with low pressure up to the north and higher pressure down to the south. Okay, so I have drawn a little map here like this. And, well, with a little map like this and those isobars on there and knowing which way is high pressure and which way is low pressure, it actually wouldn't be terribly difficult to tell you what the winds up in the free atmosphere or at the top of the Ekman layer or whatever would be doing, because if they were geostrophic, they would just be going in the direction I have of that arrow right there, where they would be parallel to the isobars with lower pressure to the left and higher pressure to the right. That would be the direction of my wind, up in the free atmosphere or at the top of the boundary layer or whatever you want to say. All right. Again, notice I've got that Ekman spiral on there, but I've blurred it out. I don't want you to see it just yet, but I want to kind of keep it in mind. Now, if I were to say, well, what about the winds just below the top of the Ekman layer? Up high in the Ekman layer. Well, a little closer to the ground, the wind is going to be a little bit slower, the vector is a little bit shorter, and it's going to be slightly crossing the isobars from higher pressure towards lower pressure, like that wind I have drawn in there that says wind near the top of the Ekman layer. Okay? Again, I still have that kind of grayed out there, kind of blurred out in the background there, but I noticed we're kind of starting to see some shape here. I mean, like if I took another place, like the wind near the middle of the Ekman layer, where the middle of the Ekman layer, the winds are even slower, that vector is even shorter, and than it was when it was geostrophic, and it's pivoted even farther across the isobars. It's crossing the isobars at an even greater angle. Okay? And in fact, if I went near the bottom of the Ekman layer, I would have the winds being even slower, the vectors even shorter, and even pivoted more to be crossing the isobars. And so you can see how at different heights at that same location, that blue dot there, at different heights in the Ekman layer, we have slightly different ideas about what this, well, not even all that slightly, quite different ideas about what the wind speed should be and what its direction should be. And in fact, look on there. See how the end of each of those vectors kind of touches that spiral that's sort of grayed out back there, or blurred out or whatever? That's what the Ekman spiral is. The Ekman spiral is this shape that explains how at different heights, where will the endpoint of these vectors be? Okay, so up high, the endpoints of the vectors are way out and straight off to the right on this diagram here. And then at different heights, as you get closer and closer to the ground, the winds are turned farther and farther to the left, and the wind vectors are shorter. That is really cool. There's actually a whole lot you can learn from the Ekman spiral that we're going to be getting to in other modules. But there are a couple of weird things about the Ekman spiral that aren't exactly thrilling. Like, for example, notice that the Ekman spiral would actually predict that the wind speed would get all the way to 0 at the surface. Well, the Ekman spiral applies to the Ekman layer, and in the Ekman layer doesn't go all the way to the surface. So you can kind of like cover up the bottom part of that diagram there. We don't go all the way to the surface anyway, so in the Ekman layer, so that idea that it somehow predicts the wind would be 0 at the surface isn't relevant. You might think this word spiral to describe this thing is kind of weird, considering it isn't really all that spirally, although there is kind of a little spirally curly Q over there on the right-hand side of the diagram. That is not real. The Ekman spiral predicts that the winds would do this sort of look, the wind vectors would become actually a little bit faster than geostrophic. The very cool word is super geostrophic for a little while, and then the winds would actually start crossing from low pressure towards high pressure. That does not happen under these conditions, but notice that the wind that we're talking about there would be almost exactly the same as the geostrophic wind. We don't measure wind as accurately as that anyway. Don't worry about that. That little curly Q at the end of the diagram isn't real. Don't worry about that. Okay. For what it's worth, your book actually even throws out that the Ekman spiral is actually a graph of an equation. In fact, it gives you the equation here, and it's a fairly messy equation that's hard to work with, because it gives you the Ekman spiral in terms of like the u and v components of the vector, u being, in this case, in parallel to the geostrophic wind, and v being the component perpendicular to the geostrophic wind. That's all really hard to think about. And it's got this lowercase gamma in it that your book explains what's going. And it has this UG, where UG is the speed of the geostrophic wind. It's a mess. Doing the math of the Ekman spiral is not really what I want to do here. Okay? I want you to understand, though, when you're looking at the Ekman spiral, nothing is spiraling. Okay? Don't get the idea that, like, if you let go of an air part, like you started an air parcel and you tracked it, it's moving in a spiral or something like that. No. The Ekman spiral is just showing you at different heights in the Ekman layer, the winds are moving in different directions, and in fact, as you go up, like the vector that is the wind at each of those heights is sort of curving as you go up with respect to height. It's showing you what the winds are doing at different heights in the Ekman layer under specific conditions. Now, applying this in a kind of thought process kind of way is not so bad. I mean, if I just sort of, again, I just swiped a slide from the geostrophic wind lecture here, and I've got a wind, and let's just say we're talking about winds like up in the free atmosphere that are geostrophic, and I've got a wind vector that is parallel to the isobars with low pressure to the left, high pressure to the right. I could sort of, in a thought process sort of way, think about it like I'm taking my little Ekman spiral diagram, and I'm going to move it to be so that the one end of the spiral, the origin of the spiral, is actually on my air parcel. I'm going to turn it and scale it so that the Ekman spiral, the end of it, matches up with my geostrophic wind vector. Here, I'll zoom in using my little magnifying glass here. If you kind of as a thought process did that, well, now at any given height above the ground in the Ekman layer, you now know what the wind is going to be, because you would just say, oh, look, at some particular height z, z being our measure of how high above the ground we are, at some particular height z, I could do the math or whatever and figure out, oh, look, that's the direction and speed of my wind at that location there. Doing in kind of a thought, oh, and look, at this height the winds are closer to geostrophic, at this height the winds are farther from geostrophic or more ageostrophic. The ageostrophic component is larger, whatever you want to say. So at least under those conditions, you would now know the direction and speed of the wind. Kind of doing it in a thought process like that, oh, I see how I'm applying this, and I'm getting winds that are curving in, that are pivoting in towards the area of low pressure. Doing it in a thought kind of way, kind of a mental little exercise, is no big deal. Doing the math is a pain in the butt, because these equations that are for the Ekman spiral are no fun. Because the U does not mean U in the usual sense of the word U as in the west to east component of the wind, and that V doesn't mean the usual sense of the word V in meteorology, meaning the north and south component of the wind. Rather, remember this crap of the U is in this case parallel, the component of the wind parallel to the geostrophic wind, and V is the component of the wind perpendicular, and that UG is not the same UG he had in that earlier equation that was for the equations of the geostrophic wind. Those are the same equations we saw last time. Rather, it's the speed of the geostrophic wind, so you'd have to compute the two components of the geostrophic wind and then use Pythagorean theorem on it. The point is, it can be done. It's an interesting computing exercise or a spreadsheet exercise, but it's not really where I want to go with this. And besides, I don't want to take the blame for it when it's a hard homework cassette. I want you to go ahead and blame this guy, Ekman himself. I have to admit, I have no idea how you pronounce his first name, von Walfried Ekman, who was the guy who discovered the Ekman spiral. Although how he did it is kind of a curious story, because he did not actually originally think about this in terms of the atmosphere. The Ekman spiral actually continues down into the ocean, affecting ocean currents below the surface. Good old Ekman is an interesting guy. He was an oceanography student who was on a research ship in the early 1900s that was up near the North Pole, and his professor gave him an interesting challenge. If you actually take a look at how icebergs move in the ocean, you find out that they do not move in the direction the wind is blowing. And icebergs do not move in the direction of the current at the surface of the ocean either. They move in a slightly different direction. And Ekman is the guy who figured out it's because those are not the currents that are affecting the motion of the iceberg. It's the ocean currents a little deeper from the surface, and he showed how the winds, how whatever the wind is at the surface and whatever the surface ocean current is, it actually, as you go deeper and deeper in the ocean, the currents turn. And they, in fact, spiral. They actually spiral the opposite direction of what they do in the atmosphere and all that kind of stuff. And the Ekman spiral, if you look at that diagram over there on the right side, in the ocean, it's really clear and it's really spirally. The ocean currents actually do make, like a spiral staircase type shape as you go down deeper in the ocean. And he showed it just depends how much of the iceberg is below the water and what the current is doing down there. Anyway, I just wanted to illustrate that for you there. That's where this idea comes from. The Ekman spiral is actually really fascinating in oceanography. It has a lot to do with where fishing happens in the ocean. It has a lot to do with how storm surge happens during a landfalling hurricane and so on. All that is Ekman spiral stuff, but we're just looking at the application of Ekman spiral to the atmosphere in this case. Now, what we did in this lecture here, these 3 parts here, was to talk about how the winds in the Ekman layer were structured in terms of how their wind speed changed with height and how their directions changed with respect to height under very specific conditions, namely statically neutral. In future lectures, we're going to be talking about what that, well, actually it's not in this module. In future modules, we'll talk about how that will change at different times of the day or under different weather conditions or so on, where the conditions are different than statically neutral in the boundary layer. And we'll also in a future lecture, future module actually, going to talk about that last, 50 to 100 meters or so down near the surface of the Earth, the so-called surface layer, and how the winds in that part of the atmosphere are structured. Now, in your textbook, the author goes off on this weird idea of calling this stuff geostrophic winds down here in the boundary layer, and goes so far as even talking about some quantities. I think he called it the geostrophic velocity. You'll notice I haven't actually showed you this. If you actually do the readings, you'll see that there's some equations and so on that we're not even talking about. One of which he even says that is one of the 2 most important equations in boundary layer meteorology or whatever. The reason why we're not showing that is twofold. First of all, threefold. First of all, I hate that term geostrophic in this concept. B, that equation is full of symbols you don't know yet. You'll know about it after Module 4. And C, we're not applying that at this point anyway. At this point, that term, that geostrophic velocity, isn't something we're using anyway. So we'll come back when we get to the stuff in the modules to apply that. So that stuff, again, it's like G equals, I can't remember the equation number off the top of my head. That is not important at this time. Okay? Alright, end of this lecture. Let's do 3 quick questions that measure your knowledge of this stuff. Remember, I can't see what your answers were, okay? I'm not smart enough to know how to rig that kind of thing up. I don't have any idea on the software. Well, I wrote the software. I don't know how to make it, so it tells me what you did. Alright, question 5. Through most of the depth of the Ekman layer, winds flow A, exactly parallel to isobars with low pressure to the left of the flow, B, exactly parallel to isobars with low pressure to the right of the flow, C, slightly to the left of what their direction would be if the flow were geostrophic, or D, slightly to the right of what their direction would be if the flow were geostrophic. Whew, think about that. That's going to take some visualization. Go ahead and make a choice from those 4 options and get some feedback before you move on to the very graphic question 6.